In this section, we're getting into the section 3, the mole conversions. And I should tell you now that it's nothing new that we haven't seen. We're really going to be taking our first section and the second section, and we'll be combining the two concepts, and we'll be scaling up our conversions and going into a full mole conversions. And so you'll see what those are all about in this section. We're just going to go over an example, really. And we'll start it off with this graphic right here, and I really highly suggest that you copy this one down, save it in your notes, and commit it to memory because it's the most important thing we will see in this unit. Really, if you can read this graphic, if you know what it means, you understand it, and you can apply it to your problems, then you should have no problem in solving any of the problems. Even though they may look confusing, it'll be talking about molecules and moles and grams. It's all contained in this graphic. So if you can read it, you'll be good. So let's talk about what's going on here. Notice that there's three sections in the center that I have here. So you can have atoms and molecules, you can have moles or grams. So these are the three types of information that we can gather from a problem and that we can change into. Really, if we just know one of these values for any substance or any compound, then as long as we know Avogadro's number and the molar mass of that compound, then we can convert in between any of these three sections. And it all takes is just either a multiplication problem or a division problem if you just know in which way you're heading and which way your units are changing. So let's go ahead and get into a problem so we can see this in action. This problem reads, how many moles of silicon are present in a sample of 9.99 times 10 to the 52 power number of atoms? And just as a reminder, I know that these numbers seem complicated, but remember that this is just scientific notation. It's a way of writing these numbers shorter. The value on this is really just 9.99, and we're just saying that there's 52 zeros behind it, but so we don't have to write out 52 digits to go with this one. We'll just use scientific notation, and if you know how to put it into the calculator, it makes this a lot easier on you. All right, so if we're setting up a conversion problem to go with this, there's just one thing we need to know right away, and that's the value from the problem. So we just copy that down. 9.99 times 10 to the 52nd power, and the unit that goes with it is the number of atoms. So we'll set up a conversion table around that. In this case, ignore the numbers right now. Just focus on the unit and transfer that over to the bottom. And to go along with that, I'll add Avogadro's number because I know that this many particles goes along with 1 mole. That's what we're trying to convert on this one. How many moles of silicon do we have from this number of atoms? So we're using this as a conversion factor for this problem. And the way that it's set up here, if I have atoms in the top left and atoms to the top right, these units will cancel out. And now the last remaining unit that I have is just moles all by itself. So if I go through this, I make my calculation, I'll be getting the result of 1.65 times 10 to the 29th power number of moles. Now, if we take it back to this graphic and see what's going on, let's see if what we did with our units actually matches up with what the roadmap is telling us. So again, we started with the number of atoms in this one. So here we are on the left, number of atoms, and we want to move it over to the moles in the center. We're moving to the right, so we'll find some arrow that tells us that. There's this top arrow starting from atoms and moving to moles, and it's telling me to divide by the Avogadro's number, and that's exactly what I have on here. I have my starting amount here on the top, and I have Avogadro's number on the bottom, so I'm dividing by Avogadro's number to get this result in the number of moles. So that works out. Now, the other way to look at this problem is that if we started with the number of moles, we'll be working backwards on this one. So again, if we're starting with the number of moles, we'll set up a conversion around that, and set at the bottom, set at the bottom that we have moles, and we're converting that to our number of atoms. And again, the number of atoms for our conversion factor is the Avogadro's number, 6.02 times 10 to the 23rd number of atoms. So when we set up this way, notice that moles here on the top left and on the bottom right, they match, so they cancel. So we're left with these two numbers, 1.65 times 10 to the 29th power multiplied by 6.02 times 10 to the 23rd number of atoms. And if we do that, we're back to our original amount of 9.99 times 10 to the 52nd power number of atoms. And now taking it back to this graphic over here, again, in this section at the bottom, we started with the number of moles. So really we're starting in the center section right here, and we are moving towards number of number of atoms. And so if you follow this arrow, we have here this arrow from moles to atoms, and we are multiplying by Avogadro's number, and that's exactly what we set up on this table too. So you can see that this graphic goes really hand in hand with the table, and it's really another way to keep all your units in check. Make sure that you're making the right conversion at every step. And just a quick tip, remember to be using the calculator to make this a lot easier on you. Again, I know the scientific notation looks confusing, but if you just put it into the calculator using the E function, this is going to make sure that you get the right answers, and that whatever you put into the calculator is not messed up by the order of operations. So if you're using the times 10 to the raised power and then you put in your exponent, that's going to introduce a lot of error into your calculations if you're not careful about where you place the multiplication signs, or if you're using parentheses or not. So just to avoid all that, make sure that you're using this E symbol on the calculator, and the way you get it is press second and then x to the -1 power. I know that a lot of you are using your calculators on your phones, but I highly recommend that you know how to use this, because these are the calculators that you get on the test. You don't get to use your cell phones on the test, so make sure that you know how to do this second E function on your calculators. Get enough practice with it. So now we've seen an example of where we deal with atoms and moles. So now let's add grams to the mix so we can get the full picture on this. So the same type of problem, just slightly different. In this case, we're starting with the number of moles, and we're trying to answer how many grams of silicon we have. So again, same type of conversion. We'll just take 1.8 times 10 to the 29th power number of moles, and we are setting up a conversion around this. Set up the table, move your unit of moles to the bottom. In this case, 1 mole is equivalent to the molar mass of silicon. Remember that we get this information from the periodic table. So for silicon, it is 2.09, round to 2 decimal places. So we move that over. So 1 mole of silicon weighs 28.09 grams. All right, so we'll do that. We'll be canceling out our units of mole to mole cancel. And if we do this in the calculator, again, take 1.65 times 10 to the 29th power, and you multiply it by 28.09, you get the result of 4.63 times 10 to the 29th power number of grams. So again, this how it compares to our graphic, we're starting here in the center with moles, and we want to go to grams. Make sure that you follow the right arrow, and here we are following the arrow that is labeled multiply. So using the atomic mass, and that's exactly what we did. We took our number of moles, and we are multiplying by the molar mass of silicon, and we're getting our result in grams. So let's turn that around and say that we were starting with the number of grams and needed to take it to the number of moles. So again, it's the same process. We can set up our table. In this case, instead of having the molar mass on top, we're setting it on the bottom, so we can have moles on the top. In this case, grams to grams will cancel out, and we're left with moles as our last unit. You do the same math, 4.63 times 10 to the 29th power divided by 28.09 gets you the result of 1.65 times 10 to the 29th number of moles. And so if we take it back to the graphic and we see if we start here with grams, we're moving towards moles. And if we follow the right arrow, we are dividing by the molar mass, which is exactly what we set up in this section too. So far we've seen 2 examples where we go from atoms to moles and back, and then we've also been from moles to grams and back. The last type of problem that we can see is a little bit bigger. Sometimes we need to go from atoms all the way to the number of grams. But notice that there's not an arrow connecting the two. So really for these types of problems, we have to stop with moles along the way before we get it to the end of the other one. So let's go ahead and take this example. How many grams of silicon are present in a sample of 9.99 times 10 to the number to the 52nd power number of atoms? So again, in this one, notice that we're starting with atoms. Is our starting unit, and we want to get it to grams all over to the end. So if we just follow atoms to moles, and then we can go from moles to grams. So let's go ahead and see that in action, set up the conversion tables to go with it. So it's the same as the problem that we already seen before, so I've just brought it over again, where we have 9.99 times 10 to the 52nd power number of atoms, and it's divided by 6.02 times 10 to the 23rd number of atoms to get us the number of moles. So here we have 1.65 times 10 to the 29th power number of moles as our intermediate answer. Now remember, that's not our final answer. We still needed to get it to grams. So let's go ahead and follow that arrow and get it to grams. So in this case, if I bring back that second conversion table that we had, we now have our last result, 1.65 times 10 to the 29th power, number of moles, and it is multiplied by 28.09 grams, so we can cancel moles on the bottom. So multiply these numbers together, and we get the answer of 4.63 times 10 to the 29th power number of grams. And so just one last thing to point out is that notice how this answer right here is the same as this starting point that we have. So really, we could just cut out a middle step and combine these two problems where we start with 9.99 times 10 to the 52nd power number of atoms, and we are dividing it by 6.02 times 10 to the 23rd number of atoms in this one. And then we can add a second step without even having to do this first calculation, and we just extended one more where we go from 28.09 grams over 1 mole. In this case, the moles will cancel out for this one. And then we can just take these numbers, 9.99 times 10 to the 52nd power times 28.09 grams divided by 6.02 times 10 to the 23rd power. And that will get us to the same answer. But just one thing to look out for is that be very careful when you're going through the calculator on these, because if you don't use the right order of operations, it's going to give you the wrong answer. So that's why I highly suggest you just take it one step at a time, and so you're not missing any steps in between. But just one thing to point out with this one is that notice that my final answers in these two, when I took it 2 steps, I did 4.63. My result is 4.63 times 10 to the 29th power number of grams. And when I did it all in a single step without taking this intermediate answer, I get 4.66 times 10 to the 29th power number of grams. So notice that the factor is still the same, times 10 to the 29th, and the unit is still the same, time grams, but my numbers, 4.63 and 4.66, they're very similar, but they're not exact. And the reason for that is that when we get this intermediate answer, since we're just rounding it to 2 decimal places, we're losing a lot of information that comes after it. And so this really just comes down to a rounding error. So just keep that in mind for working for these two problems, is that sometimes you might have a slightly different answer, but just look to see that it's still mostly the same. Just say that it's a rounding error as long as it's very close. Now, the last section to get into is 7.4, where we define what an empirical formula is. So let's get into it. So you should know that there's 2 different types of chemical formulas that we can have. They can be either molecular formulas or empirical formulas. So let's see the 2 and see what's different about them. So when we talk about the molecular formula, it's really just all the atoms that are part of a compound. So if I were to take a compound like C4H16, this molecular formula is telling me that I have 4 carbon atoms and 16 hydrogen atoms for this compound. And now the empirical formula is a little bit different from that, is that it's not a real compound, but it's really just the smallest ratio of numbers that are possible for all of the atoms of a compound. So if we were to take this molecular formula of C4H16 and we were to make an empirical formula out of that, we would need to take our numbers and in a way factor them. So 4 and 16, they're both even numbers, so you can divide by 2, or you might realize that 4 and 16 are both multiples of 4. So if we just take each of these numbers and divide them by 4, we get the new formula of CH4, meaning that there's 1 carbon for every 4 hydrogens. And this is what we call the empirical formula. Again, the smallest ratio. And the thing to understand here is that the empirical formula is not a real compound. It's just saying that of all these molecular formulas that we can have, if they have any numbers in common, we can try and reduce them to as far as we can just to have the smallest ratio of all these different molecules.